Welcome to Spirit of Math, the channel devoted to mathematical curiosities. In today's video, we prove a remarkable identity connecting trigonometric sums and Fourier analysis. Two infinite series, this one and this one, that looks completely different, turn out to have the same exact sum, and the constant is simple constant. So we will show this curious identity. First, we will show that these two series are actually convergent. For this one, we will use a comparison test, and for this one, we will use Abel test. And to prove, we will prove that this series converge to pi minus 1 over 2 by using Dirichlet's theorem. So we will use Fourier analysis, and namely Dirichlet's theorem. And to show that this sum is equal to pi minus 1 over 2, we will use Parseval's identity. So here we will show how Fourier analysis is powerful and can give some remarkable results. So let's go. First, we will show the convergence of this series. Note that sine square n is between 0 and 1, so sine square n over n square is between 0 and 1 over n power 2. So now we know that this P series, Riemann series, is convergent, and it converges to pi over 2 over 6. It's a classical result by Euler. So by the comparison test, this series converge. So we have now shown that this series is convergent. To show the convergence of the second series, we will use Abel test for convergence of series. So let's A sub n and B sub n two real sequences. Suppose first that the sequences B sub n is monotonically decreasing to 0. This means that is decreasing series sequence, and it's converge to 0. And all the partial sum of an are bounded. So there exists a constant k such that for any n over 1 we have this inequality. With these two conditions, we can conclude that this series is convergence. This series of general term a n b n converge to a finite value. This is Abel test for convergence series, and we will use this test to show that this series is convergent. So let's we put a n equal sine n and b n equal 1 over n. This series is clearly decreasing to 0. It's easy. Now we will show that the partial sum of this sequence are bounded. So we compute Sn equal 1 plus in. So it is equal 1 over 2i, and we use that sine n is equal to a n I minus a minus I n over 2I. We use the noun trigonometric formula for sine n, and we get this sum. Now we factor here by AI, and we get this geometric sum. The same thing here, we get this geometric sum. Now we have a formula which computes this geometric sum, and the same here, and we get that Sn is equal to this quantity. Now this quantity is in the module of this quantity is less than 2, because the module of AI is equal to 1, and by the triangle inequality we get that the module of this one is less than 2. The same thing here, so we get that the module of Sn is less or equal to this constant. And we have now shown that An and Bn satisfies the condition of Abel's test, so we can conclude that our series is actually convergent. Now we will recall some basic facts about Fourier analysis. So we'll define Fourier coefficients, Dirichlet's theorem, and Parseval identity. Fourier analysis deal with the periodic function. So if we take a periodic function integrable on minus pi, the Fourier coefficient of f are defined by an is equal 1 over pi, the integral between minus pi f de x cosine nx t dx, and bn is equal to 1 over pi, the integral between minus pi f de x sine nx. They are the Fourier coefficient for n bigger than 1. For 0, we have a0 is equal 1 over 2 pi, the function, and b0 is always equal to 0. So we have, and we associate to this function an infinite series. The Fourier series associated is given by this trigonometric series. The main result in this theory is the Dirichlet's theorem. Dirichlet's theorem shows that if we have piecewise continuously derivable function on minus pi, of course, which is 2 pi periodic, then for each point x in R, this the Fourier series converge to the average of the right limit and the left limit of f at x. So we get this beautiful formula. This is an important result in mathematics in general. So the hypothesis is just to have here piecewise continuously derivable function on minus pi. Okay, now we have also the Parseval's identity. The Parseval's identities show that f is square 2 integrable on minus pi. Of course, it's periodic with 2 pi periodic, with 2 pi period. Then the L2 norm of f is equal to the L2 norm square of the Fourier coefficients. And we get this beautiful formula. This means that there is equality between the L2 norm of f and the squared L2 norm of its Fourier coefficients. Now we have recalled the main result in Fourier analysis. We will apply this to our two series. So now we will give the proof of this identity. We will show first that we have this equality by using Dirichlet's theorem, and this one by using Parseval's identity. So the problem is to choose an appropriate 2 pi periodic function which will give us these two identities when we apply Dirichlet's theorem and Parseval's identity. So we consider this function 2 pi periodic, even 2 pi periodic, given by f dx equal to pi minus 1 on 0, 1 and minus 1 on 1 pi. It's of course it satisfies all the hypotheses both of Dirichlet's theorem and Parseval identity. So the representation of this function is given here. Here is 1 is pi between 1 and between 0 and 1 it's equal to pi minus 1, and it's even, so we can complete by symmetry here, and between 1 and pi it's equal to minus 1, and we complete also by periodicity. So it's a quite simple function. Now let's compute Fourier coefficients of this function. So we have, since f is even, Bnf is equal to 0, the Bn coefficient, Fourier coefficient are equal to 0, A0f is equal to this integral, and it's easy to show that this integral is equal to 0. And in my opinion, the choice of this course has been done to get this result. So between 0 and 1 you get p minus 1, and between 1 and pi you get minus pi minus 1, and the sum will give you 0. And a and f is equal to over pi. We use here the fact that the function is even, so the integral between minus pi and pi is equal to times the integral between 0 and pi, and we get this formula. Now let's compute this coefficient. It's quite easy, since the function is constant between 0 and 1 and between 1 and pi. So we get this quantity. This function is easy to find an antiderivative of this function and this one. So we get this formula, and finally we get that this integral is equal to pi sine n over n. And we have now the Fourier coefficient of f. We have a0f equal to 0, anf equal to sine n over n, and bnf equal to 0. Now we consider the Fourier series associated to f. It's given by this formula. We use okay. Now we apply Dirichlet's theorem. since for x equal to 0, since the function is continuous at 0, we get that f0 equal pi minus 1 equal to the SF0 and SF0, we get 1, and we get this formula, and we have the first equality. Okay, now we use Parseval's identity, so we get that Parseval will give us this formula, and we need to compute this integral. It's easy to compute since f is constant. Between 0 and 1 it will give us this, and between 1 and pi will give us this, so we get this formula, and we get the second formula, and we are done. We have now shown this equality, and we have also shown how Fourier analysis can be powerful to get many value of some infinite series. Okay, now to support the channel, please like, subscribe and share, and thank you.